All right, hello everyone and welcome to today's seminar. Today is our second set of early career seminars, which we will be having on the first Monday of every month. We will be having two early career speakers talk about their recent work. Today we have Leng Ying Khoo from the University of Colorado and Nithin Sividas from Catholic University of America.
Hello everyone and welcome to today's seminar.
Sorry, the streaming came on. So for the early career seminars, each will be about 20 minutes. We'll have a question period, and then we'll move on to the second seminar at about 12:30. To make sure we stay on time, if we have an abundance of questions, we'll come back to the questions at the end of the second seminar. And I want to remind everyone, because these are early career seminars, please be constructive, ask your questions in chat, and please remain muted. With that, Xinlin, would you like to introduce Leng Ying today?
All right, good. So I'm Xinlin Li. I'm a professor in the University of Colorado, and this is my pleasure to introduce my recently graduate PhD students, Leng Ying Khoo, and she got her bachelor degree from University of Michigan, and then joined my group, 5 years ago, and she started research on like plasma sphere, plasma pulse, the interaction with the radiation belt, electrons. And then later on, she really made a significant instrumental contributions to our CubeSat mission, CERBI. CERBI is the Colorado Inner Radiation Belt Experiment, which is a successor to our previous CubeSat mission, CSSWE, and has an instrument Reptile. So today she's going to focus on her contribution work about the Jiang-4 simulation of the Reptile 2. But she has published 3 first authors papers on the plasma sphere, plasma pulse relation with radiation belt electrons. And just one general comment on the Jiang simulation is a must. Whoever wants to do any particle instrument design or X-ray instrument designs. Anyway, so the Leng Ying has run all the Jiang simulation, guided our design, also checked up the electronics testing results, talks to the engineers who designed those electronics to get the particle signals out. And so I just say, cannot be more important, I just say, Jiang-4 simulation. So they also, Leng Ying's currently, per my request, currently staying here for a few months to do the transition, pass her all knowledge, skill to my current graduate students who continue doing this Jiang simulation. And she's accepted a job at the Princeton University and going to be there in April. So good. Leng Ying, yeah, you unmute yourself.
Yeah, thank you for the introductions. And let me share my slide real quick. All right. Okay. Well, yes, thank you again for the introductions. And hello, everyone. I am Leng Ying Khoo. You can call me Leng Ying. And as promised today, I will show you some of the recent work we've done on the our new instrument called the Reptile 2. And as you can see from this long list of names here, which is all my co-author, this is a collective effort with a lot of help and support for many peoples. And I just want to give a quick shout out to my advisor, Xinlin Li, who is also the PI of this mission, and Richard Slasnik, which is one of the co-PI of this mission. Both of them have taught me a lot on this topic, and which I'm really grateful for. And I also want to take the opportunity to thank the organizer for this seminar, to give the platform for us early career folks like me to really share our work today. Well, with that being said, let's get started. So here's the outline of the presentation today. I will focus on the energetic particle in the radiation belt. Particularly, I will mention some of the unanswered questions, in especially focusing on the energetic particle dynamic in the inner belt, some of the unanswered question and why it is so challenging to get this measurement that we need to answer this question. And the second part of the presentation, I will start by introducing our new instrument, the Reptile 2, and how we can push the limit of the energetic particle measurements in the inner belt. And I'll focus on 4 key features here as listed here. And at the end of it, I'll conclude with a summary slide that sum up all our findings through this work. And here, let's just start with a very classic textbook picture of what radiation belt is. For those who are not familiar with it, this is electron radiation belt generally constitutes of inner belt and the outer belt. In between, we have the slot region, which where the flux are generally lower as compared to the inner and the outer belt. And here, because of the dipole offset and also tilt of the magnetic dipole, we also have a region called the SAA region. And this is particularly important, especially for the low Earth orbit satellites. Imagine you have this region, I should mention that the magnetic field in this region is particularly low. So you can imagine the inner radiation belt will search much lower. So if you have a satellite that's orbiting, say, around 500 kilometers, they will encounter a much higher flux in this region. And this is a region you have to be aware of, especially for folks like us who are trying to study the inner belt particles. And like I say, this is a very static picture of radiation belt. In reality, it's more dynamic than that. And here is an example coming from Reeves et al. 2016, where it's the Van Allen probe measurements. On the y-axis, we have the L shell, and the x-axis, we have the time series. And you can see that for the outer belt, we have frequent enhancement and decay is very dynamic as compared to the inner belt, which is relatively stable with occasional injection from the outer belt. And there's also energy dependent dynamic as well. And here we're showing a 50 keV electrons all the way to 1 MeV electrons flux measurements. We see that there's more frequent enhancement for lower energy as compared to the more energetic particles. And there's also more slot filling events. Particles can get much lower into to the lower L shell and even into the inner belt. But there's still some unanswered question here, and I'm trying to highlight here in this region, for example, right now it's still unclear what is the cutoff energy for a given event, especially for this highlighted event here, where you can see comparable DST events, and the solar wind condition is somewhat comparable as well. But for certain event, they are able to search much lower, and the energy that are able to get into the inner belt is also much higher for certain events and not the other. Why is that so? What is the injection mechanism? I think there's still some uncertainty and unanswered question there. And there's also one of the puzzling observations during this Van Allen probe era is why there's limited access of MeV electrons in the inner belt. And here's an example from Calibrations et al. 2019, where it shows that the enhancement, they meticulously remove a lot of the background particles and reveal this very nice dynamic where we see injections of 750 keV electrons into the inner belt. And we see that all the way up to 1 MeV, but higher than that, it seems like the MeV electron have difficulty to get into the inner belt. And Lee et al. 2017 very nicely put together the Van Allen probe and the SEMPEX era, showing you the dynamics, not just from one era during the Van Allen probe era, but also the decades before. And they did, we did see some enhancement of MeV electrons in the inner belt during the SEMPEX era. But I also want to point out that Selesnik 2015 also point out this region, especially the stably trapped MeV electrons, some of them are caused, well, majority of them are caused by the coincident response, chance coincident response that could bias or could mask our the actual dynamic of the MeV electron. Well, yeah, the bottom line here really is it's very difficult to characterize the MeV electron in the inner belt with the current measurements. And why is it so challenging? I already alluded here is the proton contaminations. The proton, here is an example from Lee et al. 2015. On the top panels, we have the electron measurements, and the bottom panels, we have the proton measurements. These are the measurements coming from the CSSWE reptile instruments. And you can see for lower energy, about 0.58 to 1.63 MeV electron, the shape of the region and also the flux level is much higher as compared to the proton. But this is not the case for MeV electron. The shape is rather similar where they're located, and also the flux level is comparable as well. And this becomes very challenging because imagine you have the detector, all you see is the energy deposit on the detector. And for the very high energy particles, they are proton, they are able to penetrate through the shielding and deposit very little energy on the detector. And it becomes really difficult for the detector to distinguish whether this is electron or this is background proton. And this is why it's very challenging to measure particle of electrons or distinguish electron from a background proton in the inner belt. The second thing to be aware of when measuring this particle is the limitation of instrument electronics. This is well known. These limitations can really affect data interpretations. And when I say a limitation, I'm really talking about pulse pileup here, for example. And this is especially true for low energy electron with high flux. Imagine with a high flux, you can have two pulses coming in very close together, and they will be disguised as will be taken as by the electronic as one single higher pulses count, pulse count. So in other words, you will end up having a much higher counts in higher energy and lower counts in the lower energy because of this pileup effect. There's also another effect called the dead time, which is very similar to the pileup, except the second pulses hit during the non-responsive time when the system is resolving the first pulse, and hence the system will ignore the second pulse and only count the first pulse, and this will lead to a loss of event, and hence that we will have a lower count than we supposed to measure. So this, of course, is a very simplistic description of what really happened. Could be much complicated than that. That's what I'm trying to say. And with all this in mind, all these challenges in mind, so how can we obtain a better result and low contamination measurements? So here I'm going to introduce to you our new mission called Colorado Inner Radiation by Experiment, also known as CIRBE. It is a 3U CubeSat. As you can see, here is our payload, which is a 1.5U solid-state telescope. This is the sole payload on board, and this will be a low Earth orbit satellite, and the ideal orbit will be sun-synchronous orbit with a desired altitude between 450 to 600 kilometers. Right now, the status, we already fully integrated the system and currently in the environmental testing phase. In terms of the launch date, potentially late 2022 is still up in the air, but the launch is manifested, but the launch date is still up in the air. Well, the science objective here is we're trying to understand, again, the formation of inner belt, trying to address the question that I touched on early on. And the goal here we're trying to focus on is 300 keV to 3 MeV electrons, with the goal to have a very fine resolution measurements for these energetic electrons. And we will also have a secondary products of energetic protons of 6.7 MeV to 30 MeV energetic protons. So here's the design of Reptile 2. And as alluded by the name, you can see that this is actually, we have a lot of heritage from the Reptile instruments that was on board the CSSWE mission. And this is the classic solid-state telescope design where we have the collimator and we have a beryllium window, the thickness about 0.3 millimeter to allow us to measure much lower energy as compared to what Reptile measure. I think the lowest that it can measure is about 580. Now we're trying to push it to 300 keV or even lower than that. We also have 4 detectors here. This is the key difference as compared to the Reptile is instead of having the whole piece as the detector, we separate them into the inner ring and the outer ring. Outer ring is also what we call the gut ring. And that is any particles that trigger the gut ring and deposit greater than a certain amount of energy will be vetoed. And that will allow us to remove some of the side penetrating particles. And Yes, so this is the first feature that I actually want to talk about is the anti-coincidence detector, which is our guard ring. So here I'm going to introduce you the GM4 simulation that I've run. All this result will be mainly from the GM4 simulation that I've run. Here I use a flat energy spectrum, and this is an example of how it looks like in the GEON simulation. I simulated 0.1 to 10 MeV electrons and 1 to 200 MeV protons, randomized the energy, randomized the angle, the incident angle they're shooting from. And this is what we got. On here, I plotted energy deposit on D3 versus energy deposit on D4. And this is everything without the guard ring trigger yet. And once we have the guard ring veto in place, now you can see that it revealed much cleaner result. And even more so when we require the first detector to be triggered, now it removed a lot of particles that coming from the back that never reached D1. And it reveals a very distinct population, the footprint of these particles. Here we have the range proton, which deposit more energy on the detector than the penetrating proton. And we can even further divide this penetrating proton into front penetrating proton, which they deposit more energy on D4 than D3, and the back penetrating proton, which deposit more energy on D3 than D4. And this, I hope this leave an impression that the guard ring is really effective at removing this side penetrating particles. And of course, this is exaggerated because we use a flat energy spectrum, but it's still the same. The gist of it remains where the guard ring is really effective at removing this side penetrating particles. And we use this characteristic that we learned from this, and we derive four logic equation, and separate this particle into four population, what we call the range proton, penetrating proton, range electron, penetrating electron population. Here's the example of it. The red one is the range proton population, and we also have the green particles, which is the penetrating proton particles. And you can see that this is the incident proton results. And you can see that some of these incident proton were accidentally bin into the electron channels. And we'll talk more about that later on. And there's also some, but most of them are still correctly categorized into their respective species channel. And especially for electron, most of them were correctly categorized into the electron channel, or only a very small amount of them get bin into the proton channels. So the third features that I want to highlight is the detailed instrument characterizations. Here, so once we have the four species, four particle types, we further divide them into different channels based on their energy deposit on the detector stack. Here we have 50 channels of range proton, 50 channels of range electron, and 10 penetrating electron channels and 10 penetrating proton channels. In other words, we have 60 proton channels and 60 electron channels in total. And here's the energy response function, which tell us the detector efficiency at measuring the particles of a certain energy for each channels. And here you can see that we are able to measure, we're able to provide 6.7 to 34 MeV protons with fine resolution. Likewise, we are able to provide about 0.3 MeV to 4 MeV electrons with fine resolution. And this is a vast improvement for Reptile. Reptile only have 3 channels and 3 electron channels and 3 proton channels. And this is also thanks to the incorporations of the pulse analysis in our classification of the particles and binding of the particles. And when I say detailed instrument characterizations, we also done this analysis for incident electron that accidentally get bin into the proton channels. And here is some potential contamination that we found through those analysis. Here is an example where we show that the incident proton that barely passed through the Berlin window and they deposit so little energy on the detector, they are disguised as the range electron. But in general, based on our analysis, the signal to noise ratio, in the sense where most of this channel are still, majority of them gonna made out of the electron. Only a few channels will have an SNR less than 1. And since the proton are generally near the SAA region, this should not be a big concern outside of the SAA region. But we will monitor this effect for sure, now that we know that there's some potential proton contaminations that could happen for these channels. Another important thing is the parallel effect, that we also estimated parallel effect using a theoretical equation. And here's the result for that. For the most part, we see that the parallel effect is insignificant for proton, but it could be a problem for electron, especially near the SAA region. But I'm not going to talk more about this since I think we're a bit close to time now. And I just want to say that a more detailed characterization of the parallel are still underway. And more details hopefully will come out soon. And we're trying to draft a game plan on how we're going to tackle that, especially near the SAA region. But outside of SAA region, so far, everything seems really good. The parallel effect is rather insignificant outside SAA. And finally, all I've talked about are the results from GM4. We also want to verify our instrument performance. So what we do is we also conducted a strontium-90 radioactive source test. And here's the expected strontium-90 source test. What we do is we place the strontium-90 source on top of the aperture of our instrument, integrated instruments, and that will give us the counts. And here's the result of that. The black line or the black dot error bar is the observed count rate from this test. And what we have to do is we have to infer the flux from this count rate and compare the flux estimate with the expected flux spectrum to see if they match up. Then it tells us that our instruments perform as expected. And if it's not, that could be a problem. But so far, everything looks good. We use two flux determination methods. One is called the bow tie analysis. One is called the least square method. And so far, both agree really well, verifying our GM4 simulation result and also the instrument performance. And here's the summary. Just want to highlight that the pulse analysis and also the guard ring can really help us to push the limit and really obtain the cleaner measurements and really push the limit from 6 channels all the way to 120 channels. And it's really important to characterize the instrument performance, and GM4 simulation has been great at that. And also, I didn't have time to really talk much about it, but flux determination is really not trivial. And so far, what we found is the generalized least square method is really a promising tool that can provide a much more well-resolved flux estimate. And with that, I'll leave it on this slide. I just want to say that all this stuff that I talk about are on our JGR Space Physics Technical Report that's currently under review. So please on the lookout for that. And you can feel free to check out this ORCID link, which I included my email, and also the Survey website there, where you can follow our works if you're interested. So thank you.
All right, thank you, Leng Ying, for a wonderful talk. We do have a couple quick questions, and we have about 5 minutes for them. So the first question comes from Eric, and it is regarding, or Eric Lund, and it is regarding the pulse pileup and dead time. So he's asking, can you comment on what your calibrations have told you about how these effects come into play for the Reptile 2 instrument as it's built? I think you touched on it a bit, but you do have a couple minutes if you'd like to expand a bit more.
Yeah, so this is based on the theoretical estimates, but we also have the calibrations as well. So far, everything seems to be really good up to the true. I think we can measure 10 to the power 5 counts per second with little or insignificant pileup effects so far. And even with that, we're still trying to come up with a game plan on how to correct that. But so far, the dead time is less of a concern. Pileup is definitely more significant as we go to a much higher counts here. But I think that's all I want to say. We're still trying to characterize. I'm still working with an instrument engineer to work on this. But yeah, we're definitely aware of this this effect and trying very hard to characterize it.
Excellent. So our next question comes from George Cuck. He's wondering, how do you guys handle backscattered electrons?
I believe when you say backscatter, you're talking about the particle that potentially, oops, let me go to this slide, that can backscatter from Brilliant window. I hope that's a suggest. But yeah, I would just go with that. Well, the way we tackle this really is through our GEON simulation, because that already taken a lot of this backscattering and all that into account. And when we have, because we are shooting at particles from all over, and since we account for that really in this energy response function, and it almost sums all this effect into this energy response functions. And when we eventually trying to determine the flux from this, from the count rate, we will take all this energy response function into account, not just those from the bore site, but those that coming from shooting from the site and all that kind of stuff. We take all this energy response into account, and that already taken care of the backscatter electron as well. So I hope that answer your questions. It's not a straightforward answer, but I hope that at least touch on some of the points.
So I have one quick question regarding the instrument itself. Is the guard ring separate detectors, or is it one detector and you have position information?
It's more, you can think of, well, they are two separated in the sense where we have the energy deposit, or the pulse informations, I guess, in the simpler language, from the detector, which is the inner ring itself, and also the guard ring is separated. They are not connected. Yes. So right. There are, you can consider them as a separate detector. Yes.
Cool. Very cool. Well, thank you for a wonderful talk. If we have any other questions, we can come back to them at the end. And so with that, we'll now move on to our second talk of the day from Nithin Sividas. And David Siebeck will be introducing him. Nithin, if you would like to start sharing your screen, and David, if you would like to begin the introduction.
Well, good afternoon, everyone. I'm Dave Siebeck, and it's a distinct pleasure to introduce our next speaker, Nithin Sividas. Nithin received his bachelor's degree in aerospace engineering at the Indian Institute of Technology in Madras, Tamil Nadu. He was involved in developing a university satellite program there. He stayed on for his master's degree in aerospace and wrote a thesis focusing on shear Alfvén wave scattering of radiation belt particles. That provided him the lead-in to move towards Boston University, where he received his doctoral degree in space physics. There at Boston University, he studied the sources and effects of energetic electron precipitation under the supervision of Professor Josh Samatar and Toshi Nishimura. While he was there, he was awarded a prestigious NASA Earth and Space Science Fellowship. He graduated in 2020, and since September of 2020, he's been here at NASA's Goddard Space Flight Center working with us on topics related to the solar wind magnetosphere interaction. And that, in fact, is the topic he's going to be speaking about today. Nithin, it's all yours.
Thank you so much, David. I'll quickly get on with the talk, but I just want to warn that it's a 20-minute scripted one. So any questions, feel free to put it on the chat. And I also like to acknowledge my co-authors that I've listed here, and many others who have been willing to, talk with me about it and give me their inputs. So heliophysics, like many other fields that study natural systems, employ regression analysis to infer how a system responds to external forcing. For example, a major question in heliophysics is how the Earth's magnetosphere-ionosphere system responds to forcing from the solar wind. Fundamentally, regression analysis is simply a method to analyze how two or more parameters are associated with each other. The most familiar form of this technique is linear regression, where we assume a linear relationship between the parameters of interest. However, nonlinear regression analysis, like many of the modern machine learning techniques, allows us to not make any a priori assumptions about the association of these parameters. One major result of such nonlinear regression analysis between solar wind forcing and the ionosphere response is the apparent observation that no matter how strong the solar wind is, there might be an upper limit to how much energy reaches the Earth's ionosphere. This is reflected as a saturation of several geomagnetic indices with increasing solar wind driving. So one such effect is the polar cap potential saturation. So solar wind electric field drives day-side magnetic field reconnection, and its effects are transmitted through equipotential magnetic field lines, leading to a convection in the polar cap ionosphere that corresponds to a cross polar cap potential. Now that's the kind of toy model that we can think of when we try to explain how cross polar cap potential is created, but at the end of the day, it's far more complex than that. And when you look at the data, it seems to suggest that the potential, the cross polar cap potential, increases linearly for low values of the solar wind driving, but it tends to saturate at high values of the solar wind driving. Now, over the past 4 decades, several theories have been proposed to explain the saturation, but there has been no clear consensus on any single theory being the dominant one. In the interest of time, we won't go through the many theories. However, we note that they can be classified into 2 major types: reconnection models and post-reconnection models. Reconnection models explain the reduction of polar cap potential as a saturation, as a reduction in the reconnection rate at the day-side magnetosphere. That is by a reduction in the solar wind magnetosphere coupling. The post-reconnection models try to explain the reduction of the polar cap potential by processes happening after the solar wind plasma reconnects with the magnetosphere, and it leads to decrease in the ionospheric convection in the polar caps. So my focus in this talk, however, is not to question these models that are attempting to explain the observations that I mentioned, but instead, I'm wondering whether our interpretation of these observations are correct. So let's go back and look at the actual measurements that these models are attempting to explain. The vertical axis represents a proxy for the polar cap potential, namely the polar cap index, which is essentially the maximum amplitude of variations observed from single magnetometers from both the North and the South Pole. The horizontal axis is the solar wind Canley electric field measured using a wind spacecraft data at L1. And it can be thought of as the upper limit of the reconnection rate. Now it is measured using the wind spacecraft L1, but it's propagated to the bow shock using propagation models that the Omni database uses. The cyan line is the line of equality between the 2 axes, and the green line is the nonlinear regression function, or the conditional expectation of the polar cap potential, given the measured solar wind electric field spanning 20 years of data. So my question is whether this nonlinear regression function here that we infer from the data is a reflection of reality or not. Can we trust this regression analysis? To answer that question, we must go back a bit and recognize that solar wind data has some important sources of uncertainty. When we talk about uncertainty measurements, we usually think of instrumental error. However, most of the error comes from the assumptions we make rather than what our instruments report. When we measure solar wind parameters, we mostly do so at 230 Earth radii upstream of the reconnection region, the L1 libration point. And hence, we do not have access to the solar wind electric field that drives the magnetic reconnection, which is much closer to the magnetopause. Hence, we assume a propagation model of the solar wind. And this assumption results in a random error in the propagation times of the solar wind. Furthermore, it takes time for the reconnection electric field or the information coming from the solar wind drivers to propagate down to the ionosphere. And space physicists usually assume a constant time interval for this propagation, and this will lead to additional uncertainty in the solar wind electric field values associated with the polar cap potential that it creates. Now, we also assume that the solar wind parameters do not undergo any changes between L1 and the magnetic reconnection point, and this is not true. There is an entire bow shock, a magnetosheath between the L1 point and the reconnection site. And within this region, the clock angle of the interplanetary magnetic field, for example, which is extremely important for the reconnection electric field strengths, can undergo random changes, thereby creating a random uncertainty in the magnitude of the solar wind reconnection electric field. Now, there are many more assumptions that space physicists make, such as reconnection happens mostly at the magnetopause nose, or that magnetopause remains stationary or has a symmetric structure, or that the solar wind is spatially uniform. All of this, at the least, leads to zero mean random errors in the solar wind parameters. So what happens when there is a random error in the input to your regression analysis? To answer this question, I think we should go back to the origin of the term regression. In the late 19th century, Sir Francis Galton, Charles Darwin's half-cousin, who's responsible for coining words like correlation and percentiles, observed that extreme characteristics in parents do not seem to be passed on completely to their offspring. In this particular example, he found that on average, children of tall parents seem to be shorter than their parents. Likewise, on average, children of short parents seem to be taller than their parents. This phenomena he named regression to the mean. This is a consequence of the fact that the height of a parent is an erroneous estimate of the genetically inherited height of a child. And there are environmental influences that can cause a normally distributed random uncertainty in a binomially distributed process of height inheritance. So Galton noticed that this is not a causal phenomena, but rather a statistical effect. And as he tried to quantify the statistical effect, he invented linear regression analysis and coined the term regression. And this was the original meaning of the term regression, that extremes tended to regress towards the mean of the distribution. The word regression now has taken a life of its own. However, I think it's useful for us to remember that hidden in that historical meaning of this word is the important concept of regression to the mean. So coming back to the polar cap potential saturation problem, what this means is that there will be a bias in the regression function due to random uncertainties in the solar wind forcing, and this regression function will be biased towards the mean of the input random variable. And the nature of this bias depends on the probability distribution of the input random variable and the nature of the uncertainty. Because the distribution of drivers is more populated at low values than high, errors in the drivers will lead to mistaking the response of a high value driver with that of a low value driver on average. And as the solar wind electric field is not normally distributed, it's log normally distributed. And since the uncertainties need not remain constant with solar wind drivers, the magnitude of the uncertainties can vary with the magnitude of the driver. The regression to the mean becomes more acute the greater the solar wind electric field, and hence your regression function can appear to have a non-linearly increasing bias or even appear to saturate. Now, if this was unclear, I will try to explain the same phenomena in another context. So in the context of measuring a time series signal, in general, a signal is a stochastic process with an underlying probability distribution and an autocorrelation function. And mostly it is the case that high and extreme values of the signal are rare compared to the average value, which is more common and lower. And in signals that are propagating from point A, where you make a measurement like the solar wind at L1, but you're interested in its value at point B, closer to you, like the day-side reconnection region, you might have some serious random errors in the timestamps that you assign to the signal. In this particular instance, let's say the timestamps are off by about 10 minutes. Hence, the measured value at a time instance shown in black is going to be different from the true value shown in blue. And in real life, you only have access to your measurements, the black line, and not the true signal, the blue line. Now say that you're interested in measuring the peak value of your signal, which is in this case 3.1 millivolt per meter, and its corresponding true value is not 3.1, it's actually 2.2 millivolt per meter. And this won't be the case always because it depends on the measurement uncertainty you have. So the question to ask is, what is the statistically expected true value given a measurement, or the most likely true value given a measurement? We can find this out by doing a Monte Carlo simulation that iterates through different hypothetical instances of measurement time errors. And what you see on the right is the conditional probability distribution of the true value given an erroneous measurement 3.1 millivolt per meter. And here the vertical axis is X, the likely true value corresponding to your erroneous measurement W, while the horizontal axis is the probability density of the true value X given the erroneous measurement W. Now, what you notice is that the expected true value given the erroneous measurement, which is the mean of this probability distribution, is much closer to the mean of the signal than your specific measurement W. And this statistical phenomena is related to the regression to the mean that Galton uncovered in the 19th century. And here the main point is, if you were to try to find the polar cap potential response to 3.1 millivolt per meter, you are in fact observing the polar cap potential response to a 1.6 millivolt per meter solar wind driving. No wonder the polar cap potential appears to not live up to the electric field that is driving the reconnection. That is, when you think the polar cap potential response you see is due to a particular solar wind reconnection electric field, that is not true. It's actually on average caused by a field value that is lower and closer to the mean electric field. Now, this was an example of how time uncertainty has an effect, but other uncertainties, magnitude uncertainties, uncertainties in the propagation, all of this have the same effect of regression to the mean. So to precisely estimate how uncertainties affect the polar cap potential response, we constructed a simple error model, which says that the uncertain solar wind electric field estimate is equal to the true solar wind electric field with uncertainty in the time of measurement, which basically comes from the lack of a perfect propagation model, and uncertainty in its magnitude, which comes from many processes that happen between L1 and the ionosphere. But a major factor is the IMF clock angle that can undergo random changes after crossing the power shock. Now, one crucial point is that this uncertainty, as I mentioned briefly earlier before, is not constant with solar driving, as we usually assume, and it varies with the solar wind driver. However, these uncertainties that we assume are based on previous literature, and we make sure that they are unbiased by itself, that they are zero mean, and they are random errors. Finally, we assume that the true solar wind electric field or solar wind driver has the stochastic properties that we observe in data. That is, it's log normally distributed and is autocorrelated with a time constant derived from the data. All variables on this right-hand side of this equation are stochastic processes, and the statistical properties of these stochastic processes are the input to our model. The variable on the left the erroneous solar wind electric field is what our model calculates. And since we have the stochastic properties of input and output, we can now estimate the nonlinear regression function. And that's what you're going to see in the next slide. So here is the result of our analysis. In this plot, the green line is the regression function from 20 years of data. We've seen this before. And overlaid, and on this plot is the results from the model. The regression function estimated from the Monte Carlo model, which is the purple line. And that seems to match surprisingly well with the nonlinear regression function inferred from the measurements, which is the green line. And what this suggests is that random error in the solar wind electric field estimates and the stochastic properties of the solar wind driver parameters might be sufficient to explain the nonlinear response of the polar cap potential that we infer from data. We should note that there will always be uncertainties in both the input and output parameters of a regression, and hence there will always be a bias in the regression function. And the extent and nature of this bias is the only question. Hence, we must correct for these uncertainties before we interpret anything about the association between the parameters on which we perform this regression analysis. So for linear regression analysis, there are methods like orthogonal regression to correct for such biases. However, for nonlinear regression analysis, we cannot use the same technique. And one of the simplest techniques we can use is called regression calibration. So if you have access to the expected value of the truth, given the erroneous measurement, we can simply transform each erroneous measurement to its expected true value. And this is a mere statistical correction, but it will provide us with an unbiased regression function. So in our case, we have access to the expected true value given the erroneous measurement using the Monte Carlo solution of the error model. So what does this regression calibration actually do to our data? So it simply shrinks the input axis non-linearly based on the assumed uncertainties. So when we do this statistical correction on the actual data, that is a solar wind electric field estimates from an L1 monitor, and we associate that with the polar cap index measured on the ground in the polar cap regions, we see that the regression function is actually linear. This could imply that when we correct for the solar wind propagation uncertainty, polar cap potential is actually varying linearly with solar wind forcing. That is, the upper limit of the energy transfer from the solar wind to the ionosphere could merely be a perception due to uncertainties in the input variable, leading to a nonlinear bias in the regression function itself. Now, this is significant if it's true, because this means that the response of the magnetosphere ionospheric system can be much higher than what the saturation of the polar cap potential suggests. If the saturation is just a perception, and if in reality the effect on Earth is linear with solar wind driving, then the effect on Earth can keep increasing with the solar wind driver. At least that's what the data would imply. Now one could think, wait a minute, if the saturation effect is just a result of uncertainty in the solar wind driver, shouldn't we see a saturation effect when we compare totally different types of ionospheric responses with solar wind driving? If so, I think you'd be right. So here is the same plot of the polar cap potential saturation on the left. The green is the regression function you'd see normally, and purple is the regression function after the calibration, regression calibration, correcting the the solar wind data. And on the right, what you're seeing is the saturation of the westward auroral electrojet strength with increasing solar wind cantilever electric field. And this was noticed by Weimer in the 1990s. And the same solar wind corrections that is performed on the figure on the left is performed on the right. And even that reveals a linear relationship for the most part between the auroral electrojet strength and the solar wind reconnection electric field shown in this purple line. Now, this is a very strong clue that what is going on with the saturation could be a statistical effect common to both these figures, namely the driver and the uncertainty in the solar wind driver. Okay, but you might be thinking, wait a minute, what about all the previous theories trying to explain the polar cap potential saturation? So here's the thing. We've been asking these models to explain an incorrect inference from observations. And they have been faithfully providing us with possible mechanisms that can indeed reduce the polar cap potential from what is expected. Now we should note that a mechanism for a reduced polar cap potential, which can totally be real, does not imply that there is evidence for an average saturation, an average upper limit to the polar cap potential. These models are just telling us about processes that can reduce the potential. There are going to be instances when the opposite is happening, and we know that the opposite happens. Some mechanisms, causes or otherwise, where polar cap potential is higher than the solar wind driving that we measure or estimate. Polar cap potential being equal to the solar wind driving that we measure even at high values. These two exist, it's just that they appear to be rare. So what we need to be asking models to do is to explain the correctly inferred data, one where we have eliminated the biases caused by uncertainties in the solar wind driver. So what does this all mean? Uncertainties in the measurement of the input to any nonlinear regression analysis can lead to a nonlinear bias in the regression function, depending on the stochastic properties of the input. When we apply this insight to the polar cap potential saturation problem, we find that the effect might be a perception caused by uncertainties in the solar wind forcing. Reducing the uncertainty will indeed reduce the saturation effect. However, we do not necessarily need to reduce the uncertainty. We can simply quantify the uncertainty and then correct for it. Correcting for the uncertainty reveals that the ionosphere response to solar wind forcing might actually be linear. Hence, it's possible that no new physics needs to be invoked to explain the saturation effect on average. Now, this work is currently going through the peer review process. The preprint is uploaded in an archive in this link here. So thank you for listening. I'm happy to take any questions, and I would be more than happy if anybody is interested in looking at the paper and giving their feedback. Thank you.
All right, thank you for a wonderful talk, Nithin. Do we have any questions? So we have one from Steve Milan. Can a cross-correlation analysis between driver and response reduce the uncertainty in the lag? Oh, sorry, Nithin, you muted yourself, or I muted you by accident. Apologies.
Okay, yeah, can you hear me?
Yeah.
So no, I do think so. Cross-correlation analysis between the driver and the response can be used to identify the uncertainty in the lag and then reduce it. And there are obviously papers that do this, and this is from where we get the information about the lag, how much lag we may have.
Okay. So I have a similar question as a follow-up to this. If you did that, and if you could reduce the bias that you're measuring or that error, will you tend to naturally get back to your purple curves?
Yes. Yes.
Yeah.
So we have done this, for example, like you can take ACE and wind satellite measurements. So obviously they don't see the same thing because the solar wind has structural variations. So if we pick the measurements that are wildly varying, and you just simply not include that in your regression analysis, you'll immediately see this bias reducing and the curves go, being less saturated and becoming more linear.
That's really cool. So I have a follow-up from Jason Durr. Is it possible that there is polar cap potential saturation that generally occurs at higher levels, even though your work has revealed that the response is possibly linear? So I guess if you move beyond the range of your corrected values, is it possible that you might eventually reach saturation?
Yes, absolutely. So what we can say is that, at the end of the day, the data might not be telling us that there is saturation. Right? I mean, the whole attempt to explain saturation was because we saw in the data that there seems to be a saturation at high values, because early studies of polar cap potential, I mean, most people thought that it's linear, you know, the electric field drops through equipotential field lines, so it needs to be linear. So yes, at the end of the day, when we get more data, maybe it might reveal that beyond even the ranges that the data we have, there is some sort of a saturation. But we may not have evidence to believe that's the case with the statistics.
Yeah, and that always becomes difficult because we don't have a lot of extreme values compared to how much quiet values we have. So we have a question from Chris Moyakis. So simulation studies have talked about polar cap saturation. Are the same uncertainties inherent there, or is there other things within models that might account for polar cap saturation?
Right. So, you know, the uncertainties are clearly connected to how we interpret the data. So, you know, when simulations, like if they attempt to see what's going on, like, for example, if Pedersen conductance increases, you see that MHD models where you have a polar cap potential reducing compared to the solar wind driving. So they are, I guess, explaining physics, you know, that can cause saturation. But complex systems like the magnetosphere, you have multiple physics acting, right? Depending on the many parameters that, you know, that exist or are forced on the system. So there might be models that can show this saturation, but there are going to be physical processes, you know, a simple, you know, equipotential drop of these electric field lines where, you know, that physics says polar cap does not need to saturate. So, and there are MSD models that show polar cap saturates even higher than what other MSD models, you know, explain. So all those physics might actually be real, but it's active or turned on depending on the state of the magnetosphere, state of the solar wind. So you're going to expect a large variation in the response.
Excellent. Thank you, Nithin. I do have a couple questions from YouTube that I missed during Leng Ying's talk. So I will ask them quickly. One question, Leng Ying, do you consider simulating the effects of the spacecraft or as well in your Geont4 simulation?
Yeah, so at the moment, no, just because it is a lot of effort, but also because we are happy with what we see so far right now, even with just the current shielding of just the reptile 2 itself. It seems like it's sufficient. We are happy with what we see so far. So no plan for that at the moment.
So the other question that we have, what is a flat energy spectrum?
Yeah, so a flat energy spectrum basically is we have equal distributions of simulated energy for the range of energy we're simulating. So for example, for electron, we're simulating 0.1 to 10 MeV. So if you take the bin of 0.1 MeV bin, we have the equal number of simulating particles within that range. It makes sense, which is not technically realistic because in space we know that there is more of a exponential spectrum, but still just to get the gist of how efficient our detector at measuring this particle, we go for the flat spectrum to give us that.
Excellent, thank you. So I'd like to take this time to thank both of our speakers again. Thank you guys for wonderful talks. It was a pleasure to have you here today. Our next speaker is next Monday. Colin Forsyth will be discussing the physical processes of mesoscale dynamic auroral forms. So hope to see everyone next week. We do have a small change in the schedule. Our next helioanalytics or Python seminar will be on March 28th instead of March 21st. And that'll be going out in our newsletter. So thank you guys again, and I hope everyone has a wonderful week.